In part one of this lecture, we'll spend more time talking about deltaG, the free energy change for a reaction, and the rich variety of information it can give us about the reaction. We'll also introduce the relationship between the value of deltaG for a reaction and its equilibrium constant. A chemical reaction, as you know, proceeds until it reaches equilibrium. The sign and the magnitude of deltaG for a reaction are indications of the expected extent of reaction. That is, when equilibrium is reached, whether you expect the system to be product favored or reactant favored, or somewhere in between. Now recall we said before that when deltaG, the free energy change, is negative, the reaction will be spontaneous in the direction of forming products, that is, from left to right until it reaches equilibrium. Well, if that deltaG value is only slightly negative, that equilibrium that's reached is just modestly product favored. However, if the deltaG for that reaction is a large and negative number, we'd say that when the reaction reaches equilibrium, it's strongly product favored, and in fact, so product favored, we could say it goes essentially to completion. If deltaG is positive, we've said, of course, before that the reaction as written from left to right is non-spontaneous. So yes, the reaction will not be spontaneous in the direction of forming products. Rather, it's actually spontaneous in the opposite direction. If that deltaG is only slightly positive, we'd say that when equilibrium is reached, that equilibrium will just be modestly reactant favored. If it's very large and positive, we'd say that when equilibrium is reached, it's so strongly reactant favored that in a lot of cases you could just say, look, the reaction as written from left to right just didn't go at all. How about if deltaG actually equals 0 for a reaction? Well, if it does, the reaction's already at equilibrium. That means that there's no tendency for it to move either toward the product side or the reactant side. Now, the ability to predict the direction and extent of a chemical reaction is important. And since most real reactions are not occurring under exactly standard conditions, while many of the tables of thermodynamic values that we use are for standard conditions, it would be handy to be able to convert standard deltaG values, which we calculate a lot, to deltaG values, that is the actual free energy change for the reaction under the current real conditions. Now the next slide has a convenient equation for converting a standard deltaG to the actual deltaG under the real conditions. So that relationship between the actual deltaG, that we'd say this is the free energy change under the current real reaction conditions, is equal to the free energy change under standard conditions plus an adjustment. Well, what's in this adjustment? There are some familiar things here. For example, we have the gas constant written in energy units. You might more often see it in kilojoules rather than joules. Of course, T is the Kelvin temperature, and Q is our friend, the reaction quotient. And you might want to recall that the reaction quotient has the same form as the equilibrium constant expression K, but the concentrations and or pressures that are included are the current actual, not necessarily equilibrium values. Well, let's look at an example. The reaction between two molecules of NO2 to form one molecule of N2O4, the equation's written right here, 2NO2 gas going to N2O4 gas, It has a negative but small standard free energy change, minus 5.4 kilojoules per mole. Of course, this means that under standard conditions, the reaction as written from left to right, meaning going from NO2 to N2O4, is spontaneous. But the modestly negative delta G would indicate that the reaction does not go to 100% completion, but rather reaches a product-favored equilibrium. So it might be more appropriate to write this equation with an equilibrium sign. Now, under standard conditions, the pressures of each one of these gases would be 1 atmosphere. Thus, if we actually calculated a reaction quotient, it would be equal to 1. Let me show you that. So remember, the reaction quotient for this reaction would look like an equilibrium constant expression. So we have the pressure of the product on the top divided by the pressure, partial pressure of the reactants squared on the bottom. And since we say we're at standard conditions, so 1 atmosphere for each of the partial pressures, Q turns out to be 1. Again, remember that Q is written in the same way as an equilibrium constant expression for K, but for conditions that are not necessarily at equilibrium. So let's substitute the values for the standard free energy change and Q into this equation up here. We're going to put in a standard free energy change and a value for Q. We'll use 298 for the temperature. And we can calculate the actual free energy change under standard conditions, 1 atmosphere of each. So we get delta G equals minus 5.4 kilojoules per mole plus this adjustment, the gas constant times the temperature times ln of Q. And remember, Q is 1. Now recall that ln of 1 is 0, so this whole term goes to 0. And so the free energy change when both partial pressures are at 1, in other words, under standard conditions, is minus 5.4 kilojoules per mole. Now, so under standard conditions, the actual free energy change is the standard free energy change. And of course, this is not exactly a surprising result. We've just shown that under standard conditions, the actual delta G is the standard delta G. Seems to make sense. Now let's explore how the actual delta G changes as the reaction proceeds, because remember, the actual delta G is dependent on the standard delta G. That won't change, but this adjustment is going to change as the reaction proceeds, because as the reaction proceeds and the pressures change, Q will change. So let's see how that works. So what I have here is a table. I've got the equilibrium written above the table here. And under standard conditions, of course, we have 1 atmosphere of NO2, 1 atmosphere of N2O4. Now let's just assume that the reaction goes to the right to reach equilibrium. Well, how do we know that? Well, we know that it should actually, because the standard delta G is minus 5.4 kilojoules per mole. It's negative. That predicts that the reaction is spontaneous as written left to right. So we know that some NO2 is going to react to form N2O4. What I'm going to do here is just arbitrarily pick some change. So let's assume we know it's going to go left to right. Let's just assume that we lose 0.12 atmospheres of pressure of NO2 as the reaction proceeds. We're just picking a spot arbitrarily. Now that means if we follow the coefficients that we gain 0.06 atmospheres of N2O4. We know that because of the 2-to-1 ratio here of NO2 to N2O4. Again, what we've done here is essentially pick an arbitrary amount the reaction has proceeded to the right. Well, At this point, we're now at non-standard conditions, but we're still not at equilibrium, and I can show you that. So at this point, we'd have 0.88 atmospheres of partial pressure of NO2 left. We'd have 1.06 atmospheres partial pressure of N2O4. From there, I'm going to calculate a value of Q, and it turns out to be 1.369. So let's calculate the actual delta G under these conditions. Well, remember, it's the standard delta G plus this adjustment. Now this adjustment this time is not going to be 0 because ln of 1.369 is not 0. As a matter of fact, it's 0.314. So what we have here is the standard delta G plus an adjustment of 0.78 kilojoules per mole. So we have an actual delta G at this point of minus 4.6. So the real delta G at this point is less than the standard delta G. I should say it's less negative. So what does this mean? It means that after the reaction has started to proceed to the right towards products, that it is now closer to equilibrium and thus less spontaneous, has a less negative delta G than when we started under standard conditions, where the delta G was minus 5.4 kilojoules. However, the reaction is still not at equilibrium. It will continue to proceed to the right, losing NO2 and forming N2O4 until this delta G value, the actual one, equals 0. That's the point at which it reaches equilibrium. So what we're going to do in kind of a thought experiment here is we're going to let the reaction continue towards N2O formation until delta G equals 0. And then on the next slide, we have a table and that'll help us to do this. What I've done here is I've written the equilibrium at the top in this orange text box and reminded you that the standard delta G is minus 5.4 kilojoules per mole at 298. And now I've introduced what looks like a fairly complicated table and an empty graph down at the bottom. And let's just start filling in the numbers here, and we can explain this as we go along. So what we're going to do is we're going to start at standard conditions. 1 atmosphere of NO2, 1 atmosphere of N2O4. So we're starting at standard conditions. And down here on this graph, you'll notice on the x-axis is partial pressure of NO2. Partial pressure of NO2 up here is 1, so I've marked it here. We'll calculate Q, which we know is 1. And we know that the actual delta G is minus 5.4 kilojoules per mole here. And this is just a rehash of the fact that initially, if we start at standard conditions, the delta G is actually equal to the standard delta G of minus 5.4 kilojoules per mole. And what I've done here on our graph on the bottom is you notice the y-axis is delta G in kilojoules per mole, and it's minus 5.4, and I've marked it with a bar graph here. Let's let the reaction proceed in the forward direction as we go down the table, meaning we're going to decrease the NO2, increase the N2O4, keeping in mind the coefficients of the equation, and then we're going to calculate a Q and a delta G as we go. Now this is a situation here that we calculated on the previous slide. We said as the reaction proceeds, when it gets to this point, the delta G is less negative, it's minus 4.62. So I've got that labeled in the graph down here. At 0.88 atmospheres of NO2, the delta G is less negative, it's now minus 4.62. Let's keep proceeding. At 0.76 atmospheres of NO2, Q would be 1.94, delta G is now minus 3.76. We've marked it on the graph down here, so delta G is becoming less negative. Let's keep going here. We'll use up more NO2, produce more N2O4. Here's the Q, here's the delta G. It's even less negative now at 0.52 atmospheres of NO2, 1.24 of N2O4. There's the Q value. Now delta G is just barely negative. So what's happening here is that the reaction is approaching equilibrium. Well, where does it reach equilibrium? Well, I had to use an Excel spreadsheet to estimate these values, and that's why, and I wanted this to be as exact as possible, so I'm using some extra digits here. But when the pressure of NO2 reaches about 0.38 to 0.39 atmospheres, Q is 8.84, and remember at equilibrium, Q is equal to K, actually Kp in this case. But how do I know that this is at equilibrium? Because the calculated delta G value is now 0 using that equation, and we've reached equilibrium. And I've marked it on the graph down here at a pressure of NO2 of 0.384. Well, now the reaction's at equilibrium. So let's continue our thought experiment. Let's let the reaction continue to proceed. And you say, well, it won't proceed, it's reached equilibrium. You are correct. We are just going to artificially keep pushing it to the right. So if we did that, and we said, well, when NO2 drops to 0.34, N2O4 is now up to 1.33, Q is 11.51, and interestingly now, delta G is now positive 0.65 kilojoules per mole. Well, what does that mean when delta G turns positive? Remember, it means that the reaction is no longer spontaneous from left to right. It's spontaneous from right to left. So what this is saying here, the delta G that we've calculated, is that we've gone beyond the equivalent of, I should say, the equilibrium point. And so the reaction is no longer going forward. In fact, it's going to go backwards to go back to equilibrium. Well, let's keep pushing this somewhat silly scenario farther. Let's push the reaction farther. If we keep pushing it farther, delta G becomes more and more positive. So again, the forward reaction, left to right, is now becoming more and more non-spontaneous, which means the reverse reaction, going from right to left, is becoming more spontaneous, because if we started here with these conditions, the reaction equilibrium will say, well, I got to shift to the left. I got to go back and make reactants to go back to reach equilibrium where delta G would be 0. We'll keep pushing this here, and you see we can get the positive delta G all the way up to 6.93 kilojoules per mole. So again, the reaction starts out under standard conditions wanting to go to the right, because that's what the delta G would tell us. As it goes to the right, the tendency to go to the right decreases, the delta G decreases until it reaches equilibrium. If we actually somehow artificially made the reaction go beyond the equilibrium point, the delta G's turn positive, which means it's telling us, hey, we no longer want to go to the right, we meaning the reaction, we want to go to the left, back toward reactants, NO2. So remember, this is very similar to trying to decide in previous modules in which direction a reaction would proceed to equilibrium. So, to summarize so far, the actual delta G for a reaction is equal to the standard delta G plus an adjustment. Well, when a reaction reaches equilibrium, as you saw on the previous slide, deltaG equals 0. And that means that Q, the reaction quotient, actually equals K. So if I put 0 in for deltaG, that means we're at equilibrium. And I put K in for Q, which means we're at equilibrium. This equation here turns into this, which means we can solve for deltaG, and we can see that there's an actual direct relationship between the standard free energy change and the equilibrium constant K. Well, this equation makes sense, especially this negative sign here, because if you remember in our early lectures on equilibrium constants, we said that a large equilibrium constant indicated that the reaction is highly product favored at equilibrium. Well, if you look at this equation here, a large K value would give us a large negative deltaG, which is also saying the same thing, that the reaction is spontaneous toward products and that it's highly product favored, especially if the deltaG value is large and negative. Let's do an example calculation. Let's calculate the equilibrium constant K for our equilibrium, 2NO2 and N2O4. Now on the previous slide, we actually implied, if not stated, that at equilibrium Q equals K, so the Q was around 8.8 at equilibrium, so that's what the K value should be, but let's just calculate it straight up from this equation here. What I'm going to do is solve for K, actually ln of K first, so I'll have deltaG at standard conditions divided by minus RT. If I put in our numbers, I get 2.18, and so ln of K equals 2.18, and of course taking the exponential of both sides, we get a K value of e to the 2.18 or 8.8, and of course this result's identical to that obtained by calculating Q at deltaG equals 0 in the table on the previous slide. Remember, the reaction quotient equals the equilibrium constant at equilibrium. Well, let's look at the big picture here. The equilibrium constant K for this reaction, which is 8.8, while greater than 1, is still quite small, and this would indicate a modestly product-favored equilibrium. This is consistent with our small negative deltaG, which indicates that the reaction is modestly spontaneous. The table on the previous slide shows that the reaction comes to equilibrium when about 62% of the NO2 has reacted. So this reaction is product favored for sure, but not by much. Well, let's look at the calculated equilibrium constant values for 3 previously discussed reactions that have a range of standard deltaG values. Remember our explosively spontaneous reaction of hydrogen with oxygen to give water. Then there's our decomposition of solid N2O5, and finally our reaction of nitrogen and oxygen to give NO2. The standard deltaG for the hydrogen-oxygen reaction is minus 474. It's very large and negative. If you calculate the K using this equation at 298, what you get is a ridiculously large K value. And all that means is that a very negative deltaG, very spontaneous reaction left to right, gives us ridiculously large K value, and if both of these values mean that essentially the reaction goes to completion. It's so product favored, we can assume that there's literally no reactants left when it reaches equilibrium. How about the decomposition of N2O5? Well, that's more modestly spontaneous. So it has a more modest K value. Now it's on the larger side, but it's nothing like this K value. So what we say here is a fairly negative delta G, a fairly spontaneous reaction gives a fairly large K value. So the reaction is strongly product favored, but definitely doesn't go to 100% completion. Well, how about the reaction of nitrogen and oxygen to give NO2? Well, the standard delta G here is very positive. And if you calculate K for that using this equation, you get a really small K value. Well, what does that mean? Well, a very positive delta G means that this reaction is very non-spontaneous, written left to right. So it has an extremely small K value. So in this reaction, it's so strongly reactant favored, you can see that from the K value, it could be considered to have no forward movement at all. So if you mix nitrogen and oxygen at 298, under standard conditions, you essentially get no reaction because the equilibrium constant is just ridiculously small. Now in part 2 of this lecture, we want to zero in on the temperature dependence of some of these values.